Hello, welcome to another lecture on exact solution to viscosity. Today I am going to discuss the flow in the annular gap between two concentric cylinders with relative angular motion. So, in this figure, there are two cylinders. There is an inner cylinder with a radius R1 and there is an R2. Both are concentric, having the same center. Uh, the gap between these two cylinders, that is, this gap region is filled with some fluid of certain viscosity, kinematic viscosity mu. And the cylinders are in rotating motion or circular motion. So the tangential, the motion of the rotation of the cylinder causes the fluid particles adjacent to that cylinder to move with the tangential speed. So at the fluid particle on the inner cylinder will have a velocity, a tangential velocity u theta at r is equal to r1 is r1 omega 1, and u theta at r is equal to r2 is equal to r2 omega 2. So in between, the u theta varies as a function of r. So these are the two boundary conditions for the fluid motion. So u theta is a function of r. So our aim is to find out u theta as a function of r, assuming the flow as laminar, steady, incompressible. So that means the motion is not at very large speed, so that the flow becomes turbulent. So it is somewhat a moderate speed. The cylinders are rotating, so that the flow remains in the laminar regime, and also it is steady. Also, there is no unsteadiness. That means the temporal acceleration should be zero. So and also because this u theta, the driven motion is on u theta, and there is no radial velocity. U r is equal to 0, and there is no axial motion also. U is equal to 0, and there is a circular symmetry for the 2 points at the same radius. Here and here, the 2 points at the same radius will not have a variation of u theta. U theta is a function of r only. That means in general for any variable, okay, dou by dou theta is equal to 0. So with these assumptions, we will try to simplify the Navier-Stokes equation. So first I will write the tangential momentum. Tangential momentum. And we see how the tangential momentum is getting simplified. So the equation is dou u theta by dou t plus u r dou u theta by dou r plus u theta by r dou u theta by dou theta plus u z dou u theta by dou z. So I am writing all the terms. Plus to the Coriolis acceleration is this one is equal to minus 1 by rho dou p by r dou theta plus mu into dou squared u theta by dou r squared plus 1 by r dou u theta by dou r plus dou squared u theta by dou theta squared dou theta squared, and therefore an r squared plus dou squared u theta by dou z squared, and there is minus u theta by r squared plus 2 by r squared dou by dou theta of u theta. So this is a tangential momentum equation. If you are trying to simplify this, because of this steady, this derivative is 0. U r is equal to 0. And dou by dou theta is equal to 0. U z is equal to 0. U r equal to 0. Hmm. And dou by dou theta is equal to 0. And when it comes here, this remains dou by dou theta is equal to 0. Dou by dou z is equal to 0. Dou by dou theta is equal to 0. So we get this equation as mu into kinematic first mu into dou squared u theta by dou r squared plus 1 by r dou u theta by dou r minus u theta by r squared is equal to 0. And mu is kinematics positive, which cannot be 0. So this equation can be satisfied only with this condition, this term becoming equal to 0. And also we see here that u theta is a function of r only. So the partial derivatives that are taken from the original Navier equation, the partial derivative becomes the total derivative. So you can write as d squared u theta by dr squared plus 1 by r du theta by dr minus u theta by r squared is equal to 0. This is an ordinary differential equation. And okay, if you restructure it like this, we multiply with r squared. So here r squared will be there. Here r squared. That r squared, this will go, and this one r will go, so that this can be rewritten as like this. So we have this like this. So this guy will be right here. This equals to 0. So this kind of equations in mathematics called Cauchy's equation. Cauchy's equation. Cauchy's equation. And we know that dependent variable u theta can be satisfied by a solution of the form r raised to m, where m is an arbitrary constant, and we will be able to find out if we take u theta is equal to r raised to m, we will be able to solve for m, and the values of them gives values of them give by using the values of them you get u theta satisfying this equation, and that is in the solution. What we are looking for is a function that satisfies the differential equation that can be obtained by taking u theta is equal to r raised to m. So let us try that by finding out m. So we have u theta is equal to r raised to m. So therefore, dou u theta by dou r is equal to m into r raised to m minus 1. Dou squared u theta by dou r squared is equal to m into m minus 1 into r raised to m minus 2. So we have the terms of the form r into dou u theta by dou r and r squared into dou squared u theta by dou r squared. So here there is an r and here there is an r squared because of these multiplications. So this is r raised to m into m, and this is also r raised to m into m minus 1. So our differential equation is this term is there in the differential equation. So r raised to m into m minus 1 plus this term is there m r raised to m minus u theta, that is r raised to m. This is our differential equation. So everywhere r raised to m take outside. This is m squared minus m. There's an m here. There is a minus 1. Okay, 0. So r raised to m is the solution which we are looking for. That cannot be 0 everywhere. But so this has to be 0 everywhere. Then only our equation, this is called auxiliary equation, can be satisfied only with m squared minus 1 is equal to 0, by which you get m is equal to plus 1 or minus 1 both. M can be plus 1 or m can be minus 1. So u theta is equal to r raised to plus 1 is r. Is a solution. U theta is equal to r raised to minus 1 by r is also a solution. So a linear combination of these two can be taken as the general solution. Linear combination means a constant multiplied by r plus another constant multiplied by the other solution. So this is what is a general solution. Now that this is general solution and we have the earlier the boundary condition here, boundary conditions. So use these boundary conditions, we can solve for C1 and C2. So that way we have at R is equal to capital R1, we are having this as R1 omega 1. That is this is capital R1 plus C2 by capital R1, and R2 omega 2 is equal to C2 R2 plus C2 by R2. So now there are two equations which can be solved for C1 and C2. So what do we do for to get C2 is eliminate C1. So let us have a multiplication. Okay, I will have this equation copied for the that constant. So we have copy. I will work for a copy. Mhm. This is the kind of equations. So we are having, we multiply with R2. So there is an R2, there is an R2. So this one we multiplied R1. So there is an R1, there is an R1. So these two things are same. If we subtract, now this is R1 R2, this is R1 R2, which is common R1 R2 into omega 1 minus omega 2, and these two will go. C2 is common R2 by R1 minus R1 by R2. And there's an R1 R2 here, so R1 squared R2 squared omega 1 minus omega 2. This is R2 squared minus R1 squared. R2 squared minus R1 squared. This is equal to C2. So we have the C2 like this. Similarly, we need the C1. To get C1, what we have to do is we multiply this equation with the R2. So we are having R2 here, R2 here. Sorry, sorry. We have to get rid of C2. So divided by R2. So have an R2 here, have an R2 here, there's an R2 here. Divided by R1, R1, R1. So these two things are same. Now in subtracting we get uh, uh, R1 omega 1 by R2 minus R2 omega 2 by R1 is equal to this is actually C, this is actually C1 actually. So this is some mistake, that is C1. So this is C1, then you need to go there to C1. Okay, so C2 remains. So C1. So C1 into R1 by R2 minus R2 by R1. So there is R1, R2 on both sides. So we get, so we have this. So R1 squared omega 1 minus R2 squared omega 2 divided by R1 R2 is equal to C1 into R1 squared minus R2 squared divided by R1 R2. So we get that C1 is equal to this R2 squared by R minus R1 squared is better because R2 is larger. So we will write R2 squared omega 2 minus R1 squared omega 1 divided by R2 squared minus R1 squared. So this is what is C1. So we have both C1 and C2 substituting. in this. So let me write it back like this. And this is actually this is equal to C2 and our U theta is C1 R plus C2 by R. So this makes the entire solution solution to our the flow in the annular gap between the two concentric cylinders. So U theta is obtained as a function of U theta is obtained as a function of U theta is obtained as a function of R. So at any value of R, we can find out U theta R. Next, let us check what the radial component of the momentum equation will give. So here I will see here also I will write down the radial momentum equation plus u r by dou r plus u theta by r dou ur by dou theta plus u z dou ur by dou z minus u theta squared by r. Okay, this is equal to minus 1 by rho dot p by dou r plus mu into del squared u r is there minus u r by r squared minus q by r squared dou u theta by dou theta. So in that we know steady this is 0, ur is 0, dou by dou theta is 0, uz is 0, this is there. This we will try to find out this ur is 0, so Laplacian of ur is 0, this is 0, dou by dou theta is 0. So that gives you dou p by dou r is equal to rho u theta squared by r. So now that we are having u theta as a function of r, so rho by r into C1 R plus C2 by R the whole squared. So, so rho by R into C1 squared R squared plus C2 squared by R squared plus 2 C1 C2 C1 C2 by R gets you rho into C1 squared R squared R plus C2 squared R raised to minus 3 plus 2C1 C2 by R. So upon integration, you can get how the P varies with the R. So you can get P as a function of R by integrating this C1 squared R squared by 2 plus C2 squared r raised to minus 3 plus 1 is r raised to minus 2 by minus 2 plus 2 C1 C2 and this is logarithm natural into r. So plus some constant. So this expression gradient term. So we can if we have pressure at some point when the radius is given or some okay this constant can be arbitrary or even can be taken as zero later. So this is what is okay. We'll get a radial pressure variation by this equation. So the radial momentum equation gives the pressure variation along with the annular gap. This is it. So next we'll try to find out the shear stress. The shear stress. So that is shear stress. Suppose I want to find out what is the shear stress in the inner cylindrical wall at this point. What is shear stress? So the shear stress is given by wall shear stress is given by tau W is equal to okay tau W of tau at radius R1, that is inner cylinder, is equal to mu into dou u by dou u theta by dou r, dou u theta by dou r. At any point, it is mu into dou u theta by dou r. So that is mu into dou by dou r of C1R plus C2 by R. So mu into C1 plus minus C2 by R squared. So we get so C1 and C2, it is substitute and from R1. So there's an inner cylinder, we are having an inner cylinder. So this is the center, this is the center of it, and we have this radius, and this is R1 at this point. The tau R1 is equal to mu into C1 minus C2 by R squared. We have to substitute this R squared. I have to substitute as R1 squared. That is rho W at this is at R is equal to R1. This is R is equal to R1. So I substitute that, it becomes R1 squared. So C2 by R1 squared is, can be substituted. C2 by R1 squared, can be substituted. What is C2 by R1 squared? So we are having C2 by R1 squared is C2 by R1 squared is C2 by R1 squared is equal to R2 squared into omega 1 minus omega 2 divided by substitute here. So we get the Lavoisier's stress. Now let us assume that the cylinder has a height. The cylinder has a height. So like this, let us take the cylinder has a height. The inner cylinder has a height like this. Yeah. The height is this height is h. Height of the cylinder is h, and this is the wall shear stress. Now let us consider a okay. So the toe R1 is same everywhere on the circumference. It is constant because C1 is a constant, C2 is a constant. So tau R1 is a constant. Then tau R1 into 2 pi R1 is the total circumference multiplied by H. This is going to be the force. This is going to be this is resisting force or viscous force. Resisting force or viscous force. So resisting force or viscous force is equal to mu into C1 minus C2 by R1 square into 2 by R1 into X. Into X. So, and suppose that we are rotating this cylinder, rotating the inner cylinder at an angular speed omega by using a motor or something. There's a shaft, there's a motor to use to drive this. And suppose I have a dynamometer that can measure the torque that the motor requires for driving this the cylinder or wheel. So wherein there is an outer cylinder. Okay, it's kept inside something which is having an outer cylinder, outer cylinder like this. Okay, the outer cylinder may have some depth, little depth, more depth. Maybe let this be some delta. delta. That's more, and this is what we are thinking, that it is R2 and this is R1. Okay, so there's a fluid, because there's a fluid here. For its rotation, depending upon the viscosity of the fluid, the torque requirement will be different. So we can measure the torque required for driving this. So there is that is basically the force is the viscous force over this height. That is a major viscous force like this over this height. That is the peripheral, the periphery of the cylinder, right? We have there is there will be a viscous resistance force offered because of the fluid rotation. So that is given by this. And again, okay, so we can relate, we can make a measurement of the torque required. The torque required will be related to this. Theoretically, it can be related to this, but that basically the difference is that there is the bottom wall also participates in the rotation. So there will be a viscous force on the bottom wall, or viscous force, or that is also called drag. There will be a drag force on the bottom surface. So this is also a drag. So fluid frictional force is also called drag. So here there will be a drag. So if we can find out what is the drag over the bottom surface, then let us consider this as Fv1, and there's an Fv2. There's an Fv2. What is the drag at the the base base circle of the cylinder. So if you look at that base, that is very simple fluid mechanics problem, which we can easily work out. Axis. So maybe at some radius, if we think at some radius, r, you consider a small annular split, some annular strip of radius dr, annular strip of radius dr, and here that if you draw the top view, you'll have a circle. Already that circle is here. So the bottom base is there. So we are looking at some radius r, an annular strip of thickness dr, dr. So maybe I will draw that circle, this circle. So one more circle. So there, this motion here, the velocity, tangential velocity will be r u theta. So sorry, r omega is r omega 1. So r omega 1. The velocity at this point is r omega 1. Velocity on the bottom wall is this. Let us assume that the outer cylinder is not rotating, omega 2 equal to 0. In that case, omega 2 is equal to 0. We can have this velocity on the bottom is equal to 0. So the velocity difference is r omega 1 minus 0. Let this height be delta. So this is the velocity gradient. So if we have a mu multiplied by r omega 1 by delta, this will be the drag at a point anywhere on the annular strip. So the total annular strip area is 2 pi r dr. 2 pi r dr. So that will be the force of drag force over this annular strip, and that annular strip is at some radius r. So the torque is again multiplied by r. So this is the torque. So this is a torque. This is a torque. Did I speak this by R H1? This only track force. Track force. This is only track force. Okay. If you have a motor over here, we'll be able to measure the torque. So let us relate the torque. Okay. So in that case, so this is not. So this much is this much. This much I am talking. This much. This much is the frictional force. This much is the frictional force. So viscous force. So the torque. Let me denote the torque on the bottom base cylinder is T2. T2 will be equal to U R omega 1 by delta 2 by R 2 by R dr multiplied by one more R, and the total torque can be obtained by integrating R is equal to 0 to capital R. So this is the torque required for the rotation of the bottom base circle in the fluid medium. So whereas here on the peripheral surface we are having a drag force. Peripheral surface we are having a drag force. This is the viscous drag force on the peripheral surface. So what is the torque? And that is at the same radius. So the torque T1 we can write it as mu C1 minus C2 by R1 squared 2 by R1H into R1. So the required torque required for the peripheral for the rotation of the peripheral surface allowed is given by this. This is pi. This is pi. So this integration can give the T2, that is the bottom. R omega 1 by, actually this is some delta. 2 by R into delta dr into R. So 2 by R, there's an R here, there's an R here, there's an R here, R cube is there. So mu by delta into 2 pi can be taken outside. 2 pi is taken outside. Omega 1 can be taken outside. Then remaining that R cube, so it becomes R raised to 4 by 4, that is R1 raised to 4 by 4. So 2. So that gives the 2 cancels. So mu by omega 1 by 2 delta R1 raised to 4. So this is C1 using constant C1 constant C1 constant is there so P1 is there. So this is mu into C1 minus C2 by R1 squared dou U by dou Y is going to be like that. Then 2 pi R1 into that's an H is there. So we have the total torque. The total torque T is equal to mu by 2 pi omega 1 R1 squared by delta plus mu into C1 minus C2 by R1 squared into 2 pi R1 into R1 squared H. And here C1 and C2, if you are looking at C1 and C2, there is some slight difference in there. So from our general derivation, there is slight difference in there. For this particular case, This particular case, wherein this particular case we are having, we have seen that omega 2 is equal to 0. So omega 2 is equal to 0. So this omega 2 is equal to 0. So we will have uh, this kind of an equation. So we won't require this Newton equation for this problem. We don't require the Newton equation. So UT equation is not required. So C1 and C2 are to be substituted where for this one where C1 is equal to this and C2 is equal to this because we assumed for this particular application. Actually, from the basic derivation of this U theta and pressure variation, we come to an application in which there is an inner cylinder, there is an outer cylinder stationary, and the inner cylinder is rotated by keeping a fluid and rotating the motor. And by measurement we can get the total torque, and by theory we can get the total torque as per this situation. We get the total torque. So everything is known, geometrical parameters are known, delta is known, h is known, viscosity of the fluid can be an unknown. So everything is known. If u is an unknown, this torque and this torque measured, T measured by the dynamometer can be equated here. So that you substitute the T here with the torque measured or some calibration curve is there. You substitute that torque measured, that is a theoretical torque value, substitute here. So we can find out the viscosity of the fluid. So this is an application of whatever the problem we have considered. And in this application problem, using this application is for determination of a fluid viscosity. So this is a method actually. This is a method for finding of the fluid viscosity, wherein we make the fluid filled in the gap between two concentric cylinders by keeping the outer cylinder stationary. The inner cylinder is rotated with the help of a motor, and the torque required for turning the motor at a particular omega or omega 1 is measured. And then this theory will help you in finding the viscosity fluid. So that's an application.